In this video, we're going to talk about the 2011 AP Calculus AB free response question number 5. So in this question, they say in the beginning of 2010, a landfill contained 1,400 tons of solid waste. The increasing function W models the total amount of solid waste stored at the landfill. Planners estimate that W will satisfy the differential equation dW dt is equal to 1 over 25 W minus 300 for the next 20 years. W is measured in tons and T is measured in years from the start of 2010. Part A, we use the line tangent to the graph of W at T equals 0 to approximate the amount of solid waste that the landfill contains at the end of the first 3 months of 2010. And they give us in parentheses that after 3 months that's going to be time equal to 1/4. So the first thing we really want to notice about this is that the differential equation that they gave us, dW dt is equal to 1 over 25 W minus 300. This is in terms of W, not T. Normally they give us a derivative, and if we have dt on the bottom, there should be t's on this side, but there's a W, so we have to make sure we focus on that. It's going to be very important for us. In part A, they want us to use the line tangent, so we need to know that tangent line. And typically, we're going to use point-slope form for the tangent line, but this time, because they're giving us t equals 0, it's actually going to be easier to use slope-intercept form. So, we just need to figure out what is the slope at this time t equals 0. And in the problem, they give us that dW dt is equal to 1 over 25 times W minus 300. And we're asked to evaluate this or find this tangent line when t is equal to 1/4, but there is no 1/4. That's what we're trying to approximate. Or I'm sorry, there's no t. And that's what we're trying to approximate. We need to start with the tangent line at t equals 0, but still, there's no t. So we have to use the W at that time. And at the beginning, the landfill contained 1,400 tons of solid waste. So that's what we're going to plug in for W and then find the slope at that point. So then dW dt is going to equal 1 over 25 times 1,400 minus 300. And when you work that out, you would get 44. This is the no calculator allowed section, so you would have to actually kind of think about that. You get 1,100, and then dividing by 25 cuts each 100 into 4, and then you have 11 of those, so 4 times 11 is 44. That's how I thought about that. So now we know the slope. And so our equation for W, our tangent line for W, I should say, is going to equal 1, or never mind, not 1. It's going to equal, I was going to say 1 over 25, but that's not the slope we're using. We're using 44. It's going to equal 44, which is the slope at that point, T, plus 1,400. So just to run through this again, this is the equation of the tangent line at t equals 0. Here's the slope at t equals 0 that we just calculated. Here is the y-intercept. We know that's the y-intercept because that's when t equals 0. That's the value of W. And then we're supposed to approximate when t is equal to 1/4, so we just plug that in. 44 times 1/4 plus 1,400. And so we get 1,411 here, 1,411. Again, it's the no calculator section, but they give you fairly friendly numbers here. 1/4 of 44 we know is 11, and then 11 plus 1,400 give us 1,411. And that's all we need to do for part A. It doesn't say justify or explain or anything like that, so we don't need to. Just recognize that if they ask us to use the tangent line, we want the equation of the tangent line, so we had to find the slope at that point and then use the one point that they gave us, which was 0, 1,400. And really the only trick is to recognize, oh, when I'm finding the slope, they gave me an equation in terms of w, not in terms of t, so just be careful of that. All right, on to part B. So in part B, they ask us to find this d2w dt2 situation here, and sometimes we get a little bit confused by what that means. We think, oh my gosh, am I squaring something? What am I doing? But remember, this is just the second derivative written in the Leibniz notation as opposed to the Newton notation with the double prime. We're more used to seeing a second or a third derivative in the Newton notation with just the primes. It's a little easier, a little cleaner. But this is just the other way of writing a second derivative. So the second derivative, of course, is just the derivative of the first derivative. So we start with our first derivative. Oops, need my pen, not my pointer. First derivative dw dt, and I'm actually going to distribute the 1 over 25 in here, make this a little bit clearer. 1 over 25 w minus 300 divided by 25 is going to be, well, no calculator, but 300 divided by 25. Take 100 divided by 25, 4, multiply that by 12, or multiply that by 3 rather, and get 12. Now when I take the derivative, just take the derivative like normal. The derivative of 1 over 25w would be 1 over 25, but then since it's a w and not a t, times dw dt. Need to make sure we remember our implicit differentiation there. We're differentiating with respect to t. This is a w, so I need to multiply by dw dt. And then the 12, of course, goes away because when you add or subtract a constant and then take the derivative of that constant is 0. Because I have this dw dt, I want to now plug back in my formula for dw dt. So the second derivative, this is now the second derivative, equals 1 over 25 times 1 over 25 times w minus 300. I'm going back to the original format of our derivative here. It's going to make things a little bit cleaner for what we have to do next. So as I simplify this one more step, 1 over 25 times 1 over 25 is going to be 1 over 625 times w minus 300. Okay, so that's the first part. Find second derivative. Now use the second derivative to determine whether your answer in part A was an underestimate or an overestimate of the amount of solid waste that the landfill contains at time t equals 1/4. In part A, we use the tangent line. And the way that you decide whether a tangent line gives you an underestimate or an overestimate is by looking at whether the function is concave up or concave down. Which, isn't that a happy coincidence? We just found the second derivative, which tells us whether the function is concave up or concave down. Now here's where we need to look at this second derivative, and this is why I went back to the original format of the second derivative. We know that in the beginning, the landfill contained 1,400 tons of solid waste. And then they say that it's an increasing function. So it's only going to get, the W is only going to get bigger after 1,400. So when I look at plugging W in here, 1,400 minus 300, well that's positive. Times a positive number out here tells me that this second derivative is positive, meaning that the function is concave up. As W increases from 1,400 to 1,500 to 1,600 and so on, this is going to stay positive. So we're always going to get a positive number, 1 over 625, times another positive number. This difference will always be positive. So that tells me the second derivative is always positive, so the function is always concave up, which means that I have an underestimate. And so we can write that. So we can say our 1,411 tons is an underestimate because W is always concave up. And again, we know that it's always concave up because they tell us it's an increasing function. And as W goes from 1400 and keeps getting bigger, this is always going to be a positive difference. So a positive times a positive will give me a positive, and thus I have a concave up function when the second derivative is positive. Just for a little picture so we can see why this is happening, if you have a concave up function and then you look at the tangent line, that's always going to be underneath. Whereas if you had a concave down function and then look at the tangent line, that tangent line will be up on top, which would give you an overestimate. So second derivative can tell you whether a tangent line estimate is an under or over estimate, and that's nice. All right, on to part C. In part C, they ask us to find the particular solution of W equals W of t to the differential equation we were given with initial condition W of 0 is equal to 1400. So essentially they're just asking us to solve this differential equation, which, because there's a W on this side, means we need to do what we call separable differential equation. Separate the W's and the T's. W's on one side, T's on the other. So when I do that, I'm going to divide the W minus 300 over to the other side. So we get 1 over W minus 300 dW is equal to 1 over 25 dt. I've separated W's on the left, T's on the right. And essentially I'm just dividing this W minus 300 over here and then multiplying the dt over there. Now that I have W's on the left, T's on the right, I just anti-differentiate both sides. And the antiderivative of W minus 300 is, of course, the natural log of W minus 300. Two things to say about that. One is often we want absolute value inside of our natural log, but just like we went over in the last one, we know that this difference is always going to be positive, so the absolute value does not really apply here. Also, technically I'm using U substitution or the substitution rule here, but the derivative of W minus 300 is just 1, so there's no real substitution needed. Also, a third thing is that technically when I do an indefinite integral, I should have a plus c here, but I'm going to have a plus c on the other side, and when I combine two constants, I just get another constant, so I usually just leave it as plus c on just one side. Okay. So this was the natural log of W minus 300. Then on the other side, the antiderivative of 1 over 25 is 1 over 25 t. Then here's my constant being added in. And that is the antiderivative of this differential equation. But we're not done yet. We actually want to get W by itself, and then also because it's a particular solution, we need to plug in this value of 0 for t and 1400 for W and solve. I'm going to go ahead and solve for the W first. What we would do for that, and you've hopefully done a few problems like this and you recognize the pattern. I'm going to put E as the base on both sides to cancel out my natural log. And when I do that over here, I have e to the whole thing. We have to remember it's e to this whole thing. So on the left, it just cancels out the natural log and leaves me with W minus 300. On the right, if I have e, one exponent, one base raised to the sum of these two exponents, I know that I can sort of make that a multiplication type situation. So let's show all the work here. This is really going to be e to the 1/25th t times e to the c. And if you don't remember that, if that's a little bit weird, then just go back and look up your rules for exponential functions. Typically we go sort of the other way. We go from what we have down here, the two things multiplied together, and then we combine them to make it simpler. Here we're just going backwards. We're splitting them back up. E to the c, e to some constant is going to give me another constant. So I'm just going to change the name of my constant and make it a. And that will hopefully look familiar to you. W minus 300 is equal to a e to the, let's see if I can write this better this time, 1/25, ooh, that was a good 5, t. So my c became e to the c, which then just became a, still a constant, so I just renamed it. Now, w is equal to a e to the 1/25 t, and then I'm adding the 300 to the other side. Now we need to plug in so that we can find the a. We need to find the particular solution. This right here is what we would call a general solution. I plug in this point to find the particular solution. So now I know that w is 1400 equals a e to the 1/25 times t, which is 0, so that's nice, and then plus 300. 1/25 times 0 is 0, e to the 0, anything to the 0 is 1, so I have 1400 is equal to a plus 300, subtract, and 1100 is equal to a, and then plug that in and I'll be done. W is equal to 1100, oops, forgot a 1, e to the 1/25 t plus 300. And that is our final answer. That is our particular solution. And I went through all the steps there very carefully, very slowly to show all of the work. Hopefully at this point you could kind of recognize how this is going to happen and sort of skip a few steps in between here. Most important though, you just recognize I need to separate. So separate, W's on one side, T's on the other, anti-differentiate each side, solve for W, and make sure you plug in this point to get the particular solution and not the general solution. No more constants left in here. All right, that is 2011 for your response question number 5. Hope you enjoyed it.